Hey, today we're going to discuss the square root of 2, and we're going to show that the square root of 2 is an irrational number. We're going to show it as a proof by contradiction. This is roughly the proof that the ancient Greeks discovered, more or less. It's not going to be shown uber formally, but it's more or less the proof that they came up with, although the ancient Greeks were not terribly happy about this proof. Eventually it became accepted. I want to start off by stating that I acknowledge that the special relativity video wasn't exactly up to snuff for a lot of you, and I can respect that, and I'm welcome to accepting suggestions as to how I might redo it and make it better. So I'm going to just sort of throw open. Please contact me by private message for that. Okay, let's not post it. Just go ahead and contact me by private message, and if I've redone it, it will be after this video. If I have not redone it, it will be before this video. And yeah, you know, I'm more of a math person than a physics person. I tried, and I got you know, it was a lot to fit into the little time slot. One thing I should have shown was that the vertical length that the light beam went between the mirrors, that also contracted. And that would have been important to understanding the contraction of time. But anyways, let's move on from that, and let's go ahead and discuss the square root of 2. And we are going to assume, for the sake of argument, that the square root of 2 is rational. Okay? We are going to assume that the square root of 2 can be represented as a fraction of one natural number over another natural number. So here it is right here. A over b is equal to the square root of 2. Okay, we're going to assume that. A and b, such that A and b are both, let's move this up my way here. There we go. Such that A and b are both natural numbers. Okay, we're going to start off with this assumption. We're going to see where it leads. Now, some ground rules. We want this to be, any time you have a fraction with natural numbers, that fraction has to be able to be simplified. Okay, such that A and b become relatively prime. What do I mean? Let's say I have 3 over 5, okay? And I want to, let's say I have 9 over 15, okay? And I want to reduce that, or I want to simplify that. I'm not going to leave it as 9 over 15. What I'm going to do is I'm going to note prime factors in common with 9 and 15. Well, 9 is 3 times 3, and 15 is 3 times 5. I notice that there's a 3 in common in 3 times 3 and then 3 times 5 that can cancel. Okay, just leaving 3 over 5. Okay, leaving it such that there are no prime factors in common between A and B. And that would be called a reduced fraction. Okay, so A over B is equal to the square root of 2. You would have to set it up such that A and B have no prime factors in common. If we are not able to do that, then we cannot represent the square root of 2 as a fraction, as one natural number divided by another natural number. And in fact, that's exactly what I'm going to show in this particular proof, that we cannot. It was proven well before me. But we're going to show that you cannot represent the square root of 2 as the division of two natural numbers. But let's start off assuming that we can. Okay? And we're going to, by the way, we're going to present this not really uber formally. You guys can all find the formal proof up on the internet or maybe other YouTube channels. What we're going to go for is understanding, okay? We're going to go for actually understanding the proof and not dizzying people with a lot of symbols that fly around. So those of you who are uber purists about mathematics, just bear with me on this, okay? I know that you know this already, so why are you even, you know, I mean, come on. Let's square A over B. So what's A over B altogether squared? That's going to be A squared over B squared. But to preserve this equation symbol, we would have to square the right side. Okay? Well, the square root of 2 squared is 2. So this is A squared over B squared is equal to 2. Okay? Well, we haven't lost anything on either side of the equation. And yes, we multiply both sides by B squared. We then get A squared is equal to 2B squared. So let's study this for a while. A squared is equal to 2b squared. And let's try, okay, here we go. All right. Okay, so what do we know? We know that A and B are relatively prime to one another. Okay, so we know that that's going to mean that both A and B cannot be even. Okay, if A and B are both even, then this is not reduced. This is not simplified. Okay, so if a and b are both even, then we haven't reduced it, and if we the purpose of this game here is going to be, and I'm going to give away the punchline now, is it's going to be that a and b, for this to be true, a and b must both be even. And yet for a and b to both be even, that means that we have not reduced it. And if a and b must always be even, then we can never reduce it, leading to a contradiction, a reductio ad absurdum, where we keep reducing it and over and over again to absurdity. But that would mean that we can't have it be the division of two natural numbers, because two natural numbers will always divide down to something simplified, okay, with no prime factors in common. But if it goes on forever and ever and ever, it's like the only way that could be is if there were an infinite string of prime numbers here and here, but that wouldn't be one natural, possibly, hypothetically, I don't know, but that wouldn't be one natural number over another. Okay, I won't speculate on the infinite string thing. I mean, that's not the point here. The point here is that if we demonstrate that a and b must both be even, then we have disproven that the square root of 2 is rational. Now, I just gave away the punchline, okay, so I apologize for that. I know that's no fun, but I'm going to do that so that for the purpose of clarity, so that we can follow. So let's assume three cases. The first case is that A is even and B is not even. Now, that is possible because because they don't share prime factors in common. So if A has 2 as a prime factor, then B would not, okay? So let's go down here. A is even and B is not even. Let's go down here to A squared. Well, A is an even number squared. Thus, A squared would be a multiple of 4. Well, it would have to be, right? Because 2 squared is equal to 4. So if 2 times some number equals A, then 2 squared times that number squared, whatever that other factor squared is, would be equal to A squared. Okay, and that's a multiple of 4. But notice, though, that B is not even. Okay, and notice we just have one prime factor of 2 here. We have no prime factors of 2 in B, so that's not possible, because this is a product of 4, whereas this is only a product of 2 without any other prime factors of 2 and 2b squared. So that's impossible that A could be even and B not even. What about the other way around? What if B is even and A is not even? Okay, well, let's go down here. B is even and A is not even. What do we have here? We have an odd number squared. That's an odd number. Okay, so, and that's easily provable. Just represent an odd number as 1 mod 2 and square that. Well, you'll get 1 mod, 1 mod 2. You actually get 1 mod 4, but you know what I'm saying. It would still be 1 mod 2. Okay, so an odd number squared is going to be an odd number, so that's impossible. Well, what about if A and B are both not even? Figuring, that in fact, intuitively that feels right, okay, that A and B, that neither would be even, okay? That has a kind of rightness to it. But if we go down here, maybe, possibly, to me, it would trip you up until you realize, well, wait a second, if A is not even, then A squared would have to be odd, okay? If A is not even, then A squared would have to be, that an odd number squared is odd, right? So, but here's a factor of 2 over here. So that's not possible. So in all three cases where we assume that this is a reduced fraction, we've reached a contradiction when we've gone down here, okay? So the only thing we could logically assume is that we haven't reduced it yet. That A and B still have multiples of 2 in them. But, that A and B are still even. But, well, wait a second. That would be true no matter what our A and B are. We could never reduce it to where A and B are both, we could never reduce it such that A and B are both not even, okay? And that's a contradiction because our original assumption is that we could and we can't. Thus, we have proven that that since you can never reduce this fraction, you cannot represent the square root of 2 as the division of two natural numbers. It's not possible. Square root of 2 must be irrational. And that's all I have for you today. Thank you.